All right, everyone. Welcome to today's University of Texas Energy Symposium, sponsored by the Energy Institute. So for the students taking the class, this is a reminder that the first research note is due next week, Tuesday before class. Next week's talk will be Costa Samaras of Carnegie Mellon University. He's going to talk to us about autonomous and electric vehicles and effects of decarbonizing transportation. We are scheduling, this will probably be a remote talk, but remote interactive talk. So it will be live, but perhaps him not being present. Today's talk, we have Wen Song from the Hildebrand Department of Petroleum and Geosystems Engineering. Wen is relatively new to the campus. She's been here a year, and she's working on a lot of interesting things, including what she'll talk about today, on recycling of different kinds of materials, and looking at how to get resources out of waste and how to think about resources in a more holistic way and a technical way as well, I think, probably. So let's give Wen a warm welcome, a year late to campus, and for this presentation. Thank you.
Cool. So can everybody hear me? Great. So thanks, Carrie, for the introduction. So hi, everybody. I'm Wen Song, and as Carrie mentioned, I've been here for just a month over a year, so I'm still relatively new to the campus. But it's really kind of nice to be plugged into the Energy Institute and all of the great energy research that's happening on this campus. And so what my research group studies is really understanding kind of how do we leverage small-scale problems in order to kind of address some of our large-scale energy resource recovery challenges. And so the three key points that I want you to kind of absorb today are really centered around this idea that our small-scale phenomena really dictate how we can best use and recover our energy resources. And so the first key point is that energy as a problem spans many, many different scales. And so here, right, we can talk about things like spatial scales. So in Texas, we have a lot of oil and gas, especially in the Permian Basin. Right? So these are relatively large systems. They span on the order of several kilometers, miles, what have you, right? But that's effectively 10 to the 3, 10 to the 5 meters in length scale. But at the fundamental level, right, many of our resources are dictated by what's happening within the rock that hosts these energy resources. And so many times those fundamental pore scales are on the order of hundreds of microns all the way down to a couple of nanometers, right? So those are incredibly small length scales, right? So that's 10 to the minus 9, for example. So here we're spanning a range of spatial scales in our energy systems. Similarly, we can consider the aspect of time, right? So this is something that comes up pretty often when we discuss things like renewable resources or sustainability, right? So how sustainable or how renewable resources is really determined by, how quickly can we replenish that resource in comparison to, for example, a human lifespan or the existence of human beings on Earth. Right? So, for example, wind and solar are replenished on a effectively daily basis. Right? So that to us is a renewable resource, whereas fossil fuels are replenished, but they're replenished on the order of hundreds of million years or even greater. Right? And so that, in relation to the human lifespan, right, is relatively non-renewable. We can also look at the scale of energy usage, right? So we can look at a single battery up to the scale of how much energy our society requires on an annual basis, for example, right? And so because we're dealing with this problem that really spans many, many scales, right, both in space, time, and energy, right, that really kind of opens up an opportunity for us to, if we want to understand how to best leverage this large-scale system, right, there are plenty of opportunities at this micro and nano scale that really enables us to develop some fundamental understanding of how these systems are behaving, right? And so that opens up a window of opportunity. And what my research group works on is this idea of real rock microfluidics. And so here we are developing these visualization platforms that enable us to really go into this micro and nano scale to understand how we can best recover some of our energy resources in the subsurface. And so, as I kind of mentioned, right, energy consumption spans many, many orders of magnitude. And so here, right, this is a chart of how our energy consumption has grown over the years. And you can see that prior to the Industrial Revolution, right, effectively all of our energy was coming from biomass. And with the advent of the Industrial Revolution, right, we started using more and more coal, crude oil, and natural gas, and that's really been the main driver in terms of our modernization of our society. So things like quality of life has and total world wealth has grown exponentially as well. And so here, one thing that's really important to point out is, for example, in 2020, we're using about 600 or so exajoules of energy per year. So what does an exajoule mean? So here I've noted that an exajoule is 10 to the 18 joules, but that's an order of magnitude that really means that has no physical meaning to me, at least. And so to kind of put that into perspective, right, a single AA battery, for example, stores about 10 to the 4 joules of energy in that battery. Now, what about the amount of energy that we as humans use on a daily basis? So as a human being, right, we consume on average about 2,000 calories of food to sustain ourselves. And so in comparison to a human being, you can see, right, that the amount of energy that we can store in a single battery is very, very small. And in comparison to, let's say, a vehicle, right, so a 16-gallon car, for example, right, the amount of gasoline in a 16-gallon car, right, is 10 to the 9 joules of energy, right? So compare that to how much we as humans use on a daily basis, right? That's, again, another 3 orders of magnitude. So as we start to talk about electrification of the grid, right, and renewable integration into the grid, we require a huge amount of energy storage. And so, for example, the Tesla Gigafactory is able to capture a huge amount of energy to be stored, right, so that we can supplement our renewable resources. And that's something on the order of 10 to the 13 joules, 10 to the 14 joules per year of energy stored. Now, recall that in my previous slide, right, that our energy consumption as a society on Earth over the course of a year is on the order of, 10 to the 20, 10 to the 21 joules per year, right? And so that, again, pales in comparison to how much energy we're using, right? So if we're wanting to convert completely towards renewable resources, right, that's a whole lot of Tesla gigafactories that we're going to have to bring online and quickly. And so that really brings me to kind of the research that we do in petroleum engineering is, as you can see, right, we're using a whole lot of energy, and something like 80% of that energy is coming from our hydrocarbon resources or coal. And so that really brings us to try to address this grand challenge of supplying sustainable and renewable and reliable energy to our society. And so some of the key industries that we really can't wean off of petroleum right away include, for example, transportation. So, for example, air travel, right? That's an industry that's very difficult to kind of wean off of petroleum resources right away because of the energy density that's stored within, fossil fuels. Power generation, right? As we shift away from coal, we're leaning more and more towards natural gas as a transition fuel. Manufacturing, pharmaceuticals, textiles, right? Many of these materials are derived from petroleum products. And so as a petroleum engineer, really it's our responsibility to develop these resources in a way that is sustainable. And so the two kind of key ways that we can do this is in terms of developing recovery methods that have a low environmental impact. And the second is to develop methods where we can potentially capture the CO2 that we emit and then store that somewhere for long-term storage. And so here, right, we're really dealing with a suite of problems that lie within subsurface engineering. And anytime that we discuss subsurface engineering, here again we're dealing with a system that spans several length scales, right? So as I mentioned in the Permian Basin, these are fields that are on the order of kilometers, hundreds of kilometers, right? These are very large systems. But at the fundamental level, if we want to understand how best to extract our oil and gas resources or to capture CO2 at the surface and then inject that underground for long-term storage, then we really need to have a very solid understanding of how this overall system is behaving at this fundamental pore level. And when we discuss pore level or pore scale dynamics, right, at the micro or nano scale, then we have to look at the complexities that lie within these systems. And in particular, when you're talking about micro or nanoscale systems, then the surface interactions of your materials become very dominant. And so in our geological systems, there are really two main aspects that contribute towards your complexity. And so the first is with respect to the materials that make up your reservoir. And so here, typically, we can have carbonate reservoirs where, over half of the world's oil is stored. And these are incredibly reactive systems. So if you put a little bit of vinegar on this rock material, it can start to fizz and dissolve away, right? So you might imagine that in the subsurface, that we will have to really have a solid understanding of how reactive transport dynamics behave within these carbonate materials. Similarly, we oftentimes will have clay-rich sandstone materials, and here we have very complicated surface wettability properties and sorption properties. And so we need to then, again, consider, for example, the heterogeneities that are introduced with the presence of clay particles. Third, right, this is really the material that's been driving the U.S. energy revolution. So shale materials have nanoscale pores. And so here, many of our continuum assumptions start to break down. And so the behavior of fluids within shale materials can be very different from what we know in larger spaces. And so here we need to capture kind of the fundamental nanoscale transport dynamics that are present. So here, as you can see, the rocks that make up our geological systems are incredibly complicated, but that's not all, because typically we're interested in our energy resources, which typically come from the fluid constituents within these systems. And so, right, when we're talking about an oil reservoir, we have crude oil mixed in with brine, typically, and crude oil is often these multi-component mixtures of very complicated hydrocarbons that are residing together in this same single phase. And because oil and brine don't mix, right, oil and water don't mix, then we also are dealing oftentimes with a multi-phase flow problem. Similarly, as we try to recover these resources, we might inject, surfactants or polymers or CO2 for long-term storage. Then we're also going to have to really understand the interfacial dynamics that are at play between the injected fluids and our original reservoir fluids. And so here, right, you can see that, we're really dealing with a very complicated system. And one of the major limitations in our understanding of these materials is really due to the fact that if you pick up a piece of rock, right, it's an opaque material. So it's very difficult for us to actually observe what's happening within these materials at the fundamental level. And many times in science, the first step towards understanding how a system behaves is to actually be able to observe that system. And so what our lab does is we develop these microvisualization devices that enable us to observe at the fundamental pore scale how these systems, how these fluids are interacting with the solids and how they're being transported through the geological materials. And so what we do is we start out with a picture of a rock material. So we can take any rock material that we're interested in, take an image of this material. So this here, these yellow, white, and orange patches are these solid rock grains that make up this rock itself. And the dark blue is the pore space where fluids are able to flow through. Right, so this is where your water, oil, or CO2 might reside in your reservoir. And what we can then do is effectively binarize this image into what we call a photomask. So this is effectively like a photo negative in those old cameras. Right, and we can effectively then, so we can capture the grains in the black and the pore spaces in the white or the transparent here, and we can then effectively stamp this image into our visualization devices. And so what we do is we borrow from the microelectronics industry, where we etch the pore spaces into a. Sorry about that. So we can etch this pore space region into our substrate. And so here, for example, this is a kind of a slanted view of one of these etched devices. And these are the pore spaces that have been etched away, where fluids are now able to flow through. Right? And so typically we can etch these devices out of polymers or glass or silicon, and most recently our group has been working on, has developed etching within geological materials as well. And so now, right, you'll notice that this scale bar here is about 10 micrometers. And so here we're really zooming into the pore level, and we can effectively cover this with a transparent material. So here we've chosen silicon as the base and glass as the transparent material. And so now we can throw this device under a microscope and visualize it directly using a microscope effectively. We have flow ports here to allow for fluid injection and outflow. So using this method, we can effectively create geometries of any rock material that we're interested in. So, we can work on unconsolidated sandstones. We can work on consolidated boreas sandstones that, are good for, potentially CO2 storage. We can also look at carbonate geometries, right? So this is a very versatile approach, but there's kind of one main limitation to this approach, and that is, as I mentioned earlier, the complexity of our geological materials, and especially the reaction and the surface chemistry of our geological materials, plays a very important role in terms of determining the transport of fluids within these materials. And here, right, all of these devices are effectively etched into glass or silicon. And so that is, can be representative of very clean sandstones. But if you're wanting to capture reactive transport and carbonates, or if you're wanting to capture the effect of clay particles or organics, that's effectively missing from this infrastructure. And so the next kind of key question is, what about mineralogy? Can we incorporate the representative mineralogy of these geological systems into our visualization platform? And so that's what our group works on, is really functionalizing our devices and creating platforms that enable us to visualize directly how our fluids are behaving within these, for example, clay-rich or carbonate or shale materials. So here in our group, we've worked on for example, the effect of low salinity brines within clay-rich sandstone materials. And so here I'll show you kind of some of the key results that we've found in terms of determining a basic mechanism that determines the contribution of low salinities within this oil reservoir. We can also study things like reactive transport in carbonates. So as I mentioned, if you're going to capture CO2 and store that within the subsurface, that's going to be highly pressurized CO2, and so that CO2 is able to dissolve pretty quickly into the brine. And if you have enough impurities within the CO2 stream, then your pH of that brine can be sufficiently low where the carbonate grains, so these white pieces are the carbonate grains that we've grown within these devices. But effectively, if the pH is sufficiently low, then these carbonate grains will start to dissolve as the acid comes in, and those are potentially very significant implications in terms of the security of your CO2 that's been stored. Lastly, something that we're working on very actively is in terms of the dynamics of fluids within nanoporous materials. So here we can look at, for example, in the context of shale, how fluids are able to, for example, wet some of these organic versus inorganic surfaces. So in the interest of time today, I'm going to focus kind of on that first topic of low salinity water flooding, and this is in the context of clay-rich sandstone materials. And so here, effectively, the idea is that people have shown in core flooding experiments where if you inject a brine that has a different composition than the original reservoir brine, then we can improve the overall recovery of our system by anywhere from additional 5 to 25% of the original oil in place. And so, that might not look like very much, but if you compare that to how much we're able to recover, using a high salinity brine, right, just kind of primary and secondary recovery, right, that's a pretty significant improvement. However, there's a lot of controversy in this topic because these effects have been shown to work in some experiments but not in others, in some pilots and not in others in the field, right? And so it's really kind of a mystery as to what really is governing this increase in production. And so there's been a lot of mechanisms that have been proposed in the literature to try to describe this idea. And so here I'm only showing you 3 of those ideas, but one possible mechanism is this idea of fines migration. And so here, what's happening is initially we have our sand grains and our clay particles that are adsorbed onto the surfaces of our sand grains. And because clay particles tend to be more oil wetting, then a lot of times the oil is wetted onto the surface of the clay particles. And as we start to inject brines with low salinities, then we start to cause these clay particles to detach from the surface of the quartz, for example, and with that strip off the oil that was adsorbed onto these clay particle surfaces. And so that's one possible explanation. Another kind of idea is multi-component ion exchange, where you have charged ends in your crude oil components initially that are adsorbed onto the charged edges of the clay particles. And as you introduce a brine that has potentially different types of ions present, then those ions can have a higher affinity towards the clay particle charges and replace the charged ends of the crude oil. And so there we can also release oil into the free-flowing phase. A third idea is microemulsion generation. And so here, as we inject a low salinity brine, then we increase the solubility of water in the oil phase, and we create these microemulsions that are too small even to observe really under a microscope. So these are on the order of nanometers or hundreds of nanometers. And what happens is as they are formed, then they diffuse into the pore, and at the ends of the pores sometimes we have connate water, and that is typically high salinity brine. And so as these emulsions meet the high salinity brine, then they break up and that water accumulates at the end of the pores and pushes the oil out of the pore space. And so as you can see here, there's a wide variety of mechanisms that have been proposed, but there's really no agreement in the community as to what's really driving this effect. And so that's where we thought it might be useful to kind of visualize directly how these systems are behaving at this fundamental pore level. Because all of these mechanisms that I showed previously have been proposed based on effectively core flooding experiments where you take a piece of rock, you inject from one end, you measure what comes out the other, right? You might be able to measure your flow rates and your pressures and your compositions, right? But you really have no understanding or way to observe into this rock material to really understand what's happening. And so here we set out to do exactly that. We wanted to observe directly at this fundamental level what was happening. And so to do that, we started out with our micromodel device. So here, these dark patches are the grains that make up our rock, and these lighter regions are the pore spaces where fluids can flow through, right? So here, for example, you can have brine or oil or what have you. And you can see that because this is a purely silicon device, right, it's able to capture the effects of the sandstones, but we know from the experiments that this effect is only relevant in clay-rich materials. And so here we wanted to add in clay particles into our system. And so we create a solution with kaolinite clay, and we inject that into our pore space. And so all these little black specks are the clay particles that have been deposited, and by manipulating the flow, we can coat these surfaces fairly evenly with the clay particles. And so that was really great. But before we can do any type of experiments to understand the mechanisms of low salinity water flooding here, we need to first validate that this device does in fact behave like a real clay-rich sandstone would. And so to do that, there are kind of two key parameters that we need to validate. And so the first is with respect to the wettability of these systems. And so it's known that in a clay-rich sandstone, that these materials tend to be relatively mixed wet. And so that means that, water and oil or water and air will like to occupy these pore spaces, at a similar level. Whereas an extremely water-wetting surface, right, will effectively capture all the water on the surface, and it'll be very difficult for example, air or oil to stick onto a surface. So here, we wanted to validate that aspect of our device. So, again, these are the grains. We have our pore spaces, and we have our clay particles that have been deposited into this pore space. And you can see that there are some regions where there's an extremely high density of clay particles within the pore space. And so that's something to keep your eye on. Because now, so here this is a dry micromodel. And now we're going to allow for brine to come into this system. And what we get is that the brine is effectively able to migrate through most of this pore space fairly well, but it really seems to have a lot of difficulty kind of wetting these regions where there was an extremely high density of clay particles present. And so that, is direct evidence to us that with the presence of these clay particles, we've now altered the wettability properties of our system so that, in these clay-rich regions, these are no longer water wet. And so as a system, this is a mixed wet condition. And so that's great. That checks off our first box. The second box that we needed to check off was with respect to the sensitivity of the adsorbed clay particles to changes in salinity. And so here, in a real clay-rich material, it's known that there exists a critical salt concentration where for salinities above that salt concentration, the clay particles are sorbed very stably onto the surface of your sandstone. But as you reduce the salinity below that critical salt concentration, then your clay particles will start to desorb and migrate through your pore space. And so here we can start out with a very high salinity scenario. So here again we have our clay particles, and we can then inject brines with decreasing salinities in these systems and really monitor where our clay particles are. And so effectively we do that, and we really didn't see much happening up until this 4,000 parts per million point, at which you can see that there is pretty significant migration of clay particles. And specifically, right, you can see the formation of these small pore bridging structures across these very small but high velocity pore throats. And you can also see the redeposition of previously mobilized clay particles within these larger, more intermediate velocity pore bodies. And so here we were really able to validate that, yes, our device is mixed wet, and the clay particles are sensitive to changes in salinity. So now, having validated that our device does in fact behave like a real clay-rich sandstone, we can effectively start to develop our mechanistic understanding of the low salinity effect. And so what we do is we try to first replicate what nature does. And so typically in nature, right, your sediments are deposited, and then it's compacted, and over time, right, it forms a rock. The clay particles are either deposited with the rock or it's grown in. And it's effectively deposited with your original brine. And then what happens is that oil matures from some source rock below that, and it migrates up into this pore space, right? And so this is immediately taken after that migration process, right? And the next step is a little bit tricky because typically, right, this oil needs to equilibrate with its surroundings, and it, probably has had millions of years, hundreds of millions of years to do that. And that's a little bit difficult to replicate within the laboratory. And so what we can do is we can let it, equilibrate for a couple of weeks and really monitor how our interfaces are changing or not changing. And what we find is that effectively after about 2 weeks of this equilibration process, our interfaces have stabilized. And what you'll notice is that during this equilibration process, right, that there's been a significant amount of fluid movement within the pore space. And so here, if we zoom in, right, this is immediately following that migration process. You can see that the water is occupying the smallest pore spaces here. And importantly, there are these macroscopic water films that are lining the surfaces of our solid gray materials. And so this is indicative of a highly water-wetting system. But over the course of this equilibration process, right, we start to observe that the oil is actually migrating into some of these smaller pore spaces. And importantly, these macroscopic water films that used to be present and lining the surfaces of our grains, right, are no longer visible. And so this really suggests to us that perhaps over the course of this equilibration process, that the surface interactions between the oil and potentially some of the clay particles have allowed for the oil to make direct contact with the clay particles and to alter the local wettability of this pore space. Okay. So, having achieved our equilibration process, we can use this as effectively our original reservoir. Right, so this is, if you go into, as a geologist, go out into the field and you look for these oil deposits, right, maybe this is what we expect to see before the engineer has gone down and started doing stuff with the reservoir. Right? So we can start with our initial reservoir condition, and we can effectively follow what the industry does and inject a high salinity brine into this system. And so here, right, you can see that we've created these high preferential flow paths, right? And it really looks like this brine kind of skipped over this top region altogether. There's really a lot of oil that's relatively unswept. But the advantage of visualization at this scale is that you can go back and compare this particular location to what it was before we injected anything. And you can actually see, if you focus in onto the square up here, you can see that in fact the brine did make its way through these pore spaces, but it's really just done such a poor job at sweeping that oil away that it's left a lot of these macroscopic oil films behind, right? These are very thick oil films. And even though, so effectively what we're seeing is that even though the oil, the water was able to come through here, right, the oil was adsorbed onto the surfaces of our pore spaces due to the presence of clay particles, that they weren't able to be stripped off. And so that's a main reason why our current recovery factor for oil and gas, or for oil especially, is so low. Right? And so how does low salinity brine impact this? Well, that was the kind of the central theme of this study, was understanding what low salinity brines do to our system. And you can see, first of all, that there's a lot less oil that's left behind in this system, right, after this low salinity brine. And what's important to note is that these thick oil films that were present previously, right, after the low salinity brine has come through, they are no longer visible anymore, or they're no longer present, actually. And what's important to note is that the salinity that we've injected here is at that 4,000 parts per million mark, and that was what we found to be the critical salt concentration in our system, where clay particles start to desorb from the pore surfaces and mobilize within our porous medium. Okay? And so here this effectively suggests that some of our clay particles are being stripped off of the surface. Out of curiosity, we wondered what even lower salinity would look like in this system. And what we got was something that was very surprising. So here you can see all of these droplets, right? We call them emulsions. But effectively, right, in all of our high preferential flow paths, right, we see the formation of these emulsions. And that's very, very surprising to us, because we haven't injected any stabilizing agents. We haven't injected any surfactants, for example, to create these emulsions. And in fact, these emulsions are incredibly stable. And that was very surprising, because if we just took a sample of this crude oil and, with water and shook it up, we don't expect any emulsions to form. In fact, we don't observe any emulsions that form. And the second thing that's very curious about these emulsions is that they're incredibly stable, right? So if you just took water and oil, or this crude oil and water, and shook it up in a jar, right? Yes, you can form tiny little emulsions, but after a couple of hours, all of these emulsions will kind of break, and you get your oil phase and your water phase, or water and oil, right? That's not the case here. They're stable after even a week of just kind of sitting there. And so that was very, very interesting to us and surprising. And what we think is happening is that effectively, because we're below that critical salt concentration, where clay particles are being stripped off of the surface and mobilizing within our porous medium, then the clay particles, right, are actually, so this is a classical kind of surfactant stabilized emulsion, right? What we have is that the clay particles are actually going towards the water-oil interface because of their complex charge distribution on their surfaces. They're stabilizing these water-oil interfaces and creating these Pickering emulsions throughout our system. And so we can test that hypothesis by doing some comparative studies. And so here on the left, we have a system that has no clay particles, and we do the exact same sequence of flooding. And you can see that there are no emulsions that have been formed in the pore space, and in the bulk, right, the water and the oil separate immediately. However, in the case where there is clay particles, right, we can see the formation of these dense emulsions throughout the preferential flow paths in the pore space, and we can also form them very stably in the bulk. And what's probably important to note here is that after 3 years, so this was effectively over the course of my PhD, right, we can come back to these same sets of systems, and they effectively look the same, right? The emulsions haven't broken. And so that really suggests very strongly to us that what we actually have here is the creation of Pickering emulsification within the pore space due to the low salinity effect where the clay particles are being stripped off of the walls and going to these water-oil interfaces. And so how does that then affect our long-term production of the reservoir? Well, because we're creating emulsions, right, that's a whole bunch of extra interfaces where we have extra capillary pressure to have to overcome, and so then it can be difficult to inject fluids at high rates. But the important thing here, right, is that as we form these emulsions, right, we effectively block up the preferential flow paths, and so any other fluids that we inject into the reservoir have to flow through these pockets of connected fluids, and those are where the oil is, right? And so using this, and combined with a high salinity brine where we can effectively break some of these emulsions, right, we can improve our overall oil recovery yet again. And so those are really nice pictures to kind of explain the mechanism behind this, but how does that actually affect for example, the recovery of our hydrocarbon resources? And so here, this is a very crude model of our micromodel device, right? So we can sample at, let's say, 25 fixed locations across this micromodel. So after each one of these processes, we can go back to each one of these spots and kind of monitor how that location has been evolving. And we do this so that we can average out any pore scale heterogeneities that might be encountered otherwise. And so here, for example, this, right, is the original reservoir condition at this particular spot. And these are the fluid distributions after each of these injections, right, at that same exact location. And what we can then do is leverage image processing to segment these images into our phases, right? So here the grains are depicted in black, the oil is in the green, and the water or the brine is in blue. Okay? And because our device is effectively a two-dimensional device, we can effectively use the areas of our pictures to calculate our saturations, right, our volumes. And so what we can do then is quantify, how much oil there is after each one of these steps, and we can average these across this micromodel. And what we see is that after the initial high salinity water flood that the industry currently does, right, we can recover something like 38-40% of our original resource. But with the injection of a low salinity brine, we can improve that recovery by about 6.5% of the original resource. And with this Pickering emulsification mechanism, right, we can then improve our overall oil recovery by an additional 8% of the original oil that was in play. And so that potentially has some important implications in how we operate these systems. And so just to kind of wrap up, right, in our group, we develop what's called real rock microfluidics so that we can gain these pore scale dynamic understanding of how our fluids and our rocks are interacting. we can then use these devices to discover fundamental mechanisms. So here, right, we showed the importance of our clay nanoparticles and how they stabilize these Pickering emulsions within our system. And we can then translate that towards some kind of direct impacts that the industry might be able to leverage. So coming back to our 3 key points, right? So energy spans many different length scales, and there's a lot that we don't yet know at the small scale, in particular the micro and the nano scales. And so there are a huge amount of opportunities that are available for us, as micro and nano engineers and energy resources engineers, right, to try to kind of leverage these resources. And real rock microfluidics or nanofluidics provides a potential path towards developing some of these understandings. So with that, I'd like to acknowledge my graduate students as well as our funding agencies. So thank you, and I'm happy to take questions.
Questions from the audience? Please raise your hand. I'll start with one. So I guess it's pretty cutting edge stuff, looking at pore scales, and you have a 2D device, and the pores are 3D. So what do you have any insights in what might change or what you know is different or not in the 3D world of pore space?
Yeah, absolutely. So that's a really great question. So you're right. Pore systems are 3-dimensional. Here we're really only capturing, things that are relatively 2-dimensional. We try to overcome some of those issues. So, for example, in a 2-dimensional system, right, each one of your pores are approximately connected to 3 or 4 other pores. And in a 3-dimensional system, right, you're going to have also these other dimensions. So you have a coordination number, what we call a coordination number of 6. And so we can actually manipulate our device so that each pore is in fact coordinated with, on average about 6 other pores. So that's one way of kind of overcoming this 3rd dimension. One of the advantages that we have is that because we're operating at the micro and nano scale, then gravity is not so important, especially in comparison to, for example, capillary forces. So there, we can kind of get away with it. But we do see some differences in terms of one-dimensional flow to 2-dimensional flow, right? And so I didn't show it here, but in this particular study, we started out with a single grain that was dissolving in a very nice linear channel, right? And we can then upscale that to a porous medium, and we can see that the effects, the mechanisms are present, but perhaps the degree to which this mechanism is important changes.
By switching to this new brine and introducing your emulsion mechanism, does that significantly change the material cost of the brine in industrial processes? And
if you have access to fresh water, it shouldn't. But you might want to do a cost analysis.
My question was about the high salinity brine. So why is it that the high salinity brine doesn't strip off clay particles, but the low salinity does? I didn't quite understand that part.
Yeah, so this has to do a lot with the surface charges of the clay particles and of the silica grains, right? So effectively your silica grains are negatively charged, and your clay particles, depending on the clay, will have positive charges and negative charges. And when you have a lot of salt in that system, you effectively right, you can have the salt kind of help these charges attach to each other. Whereas when you take that salt away, right, then these charges will start to repel, and that's when the clay particles will start to.
For fresh water, the clay particles will come off the fastest in that way. Okay.
Thank you so much. So I suspect it may be different for different wells, but when you have produced water that comes out, what is the typical range of salinity for that? You mentioned 20,000 parts per million, 10,000, 4,000, but what would you get from produced water? Is that the purpose of this, being able to recycle or reuse for EOR?
Yeah.
Produced water? And would you have to, kind of desalinate it just to get it to 20,000, or?
So, great question. So, the salinities of our oil reservoir brine vary very greatly. So there are some reservoirs that are like 10 times the salinity of seawater, right? So the numbers that we've chosen here were for that particular reservoir. But the critical salt concentration that we were able to identify, that's not specific to any.
But is
Any
there a
reservoir.
range? I mean, is it so variable that you can't say anything? So out in West Texas in a well, when you get a lot of produced water, is there a typical range for the brine or the salinity that comes out for the produced water?
So we're working right now with a brine that is like 10 or 50 times the salinity of seawater, but there are...
And so what is that?
It's like 10 weight percent of salt, so that's pretty saline. So you wouldn't want to use that here, for example. This is, I think, probably most applicable if you had access to fresh water.
Thank you.
With your micromodel, are we capable of varying the depth of the etching?
Yeah, absolutely. Yeah.
So theoretically, you could use the widths of the two-dimensional model that we see here on the top left. We could use that to estimate or create deeper etches or shallower etches,
Yeah,
creating a
absolutely.
three-dimensional pore
Yeah,
space.
yeah. So in fact, you could even etch these on the order of 5 nanometers if you wanted to, right? So, and then that's kind of like pseudo nanofluidics.
I guess I'll ask a question on top of that. So have you thought about, or others thought about, using selective laser sintering techniques to try to mimic
Have I?
like a selective laser sintering technique or rapid prototyping technique to mimic the three-dimensional designed pore space, since they're basically made out of fusing particles together? And that's the hard part of making metals, is to get them fully solid. So if their problem is making them solid, it's a good thing for you to understand pores.
Yeah, yeah. So we haven't done that in our group, but there are groups elsewhere that they can have effectively a bead pack of glass, and so you have a little three-dimensional structure of that, and then you can design fluids to have the same refractive index as the glass, and then you can use a confocal microscope to kind of go down in the Z direction to kind of observe where the fluid interfaces are. The challenge, if you're going to use any kind of real materials, is the opacity of these materials, and so it's challenging. But one of my students is working on kind of using an actual piece of rock material and then developing a technique to visualize into the rock pore directly.
Any other questions? Did you make up the term real rock, or is this a common?
We made it up.
Okay. Do other geologists get mad that you say you work on real rocks and they must work on some other not real rocks? I don't know. So, okay.
Well, typically microfluidic devices are glass or silicon or polymer plastics. So
Okay,
those
there
are
you
not
go.
really.
Okay. All right, now I get it. Maybe.
Yeah.
Okay, if there's not any further questions, thank you, Wen, for an enlightening talk. I definitely learned about petroleum, some rocks today, and petroleum geology. Thank you.